All right, welcome everybody. Today we're going to talk about Calc Lesson number 13, and this is section 2.3 still, and we're going to talk about trig derivatives and then the introduction to the quotient rule for derivatives. So first, let's go ahead and remind ourselves about the product rule. That's what the previous lesson was about. We're still going to see a little bit of the product rule today. And of course, as a reminder, the derivative of sum f times sum g is the first f times the derivative of g plus g times the derivative of f. And again, if you don't have your formula sheet printed out already, you should. You certainly will be expected to use the product rule on the upcoming assessment. So then we've already talked about the derivative of sine being the positive cosine and the derivative of the cosine being the negative sine. There are 4 additional formulas for the 4 remaining trig derivatives. As always, we'd be happy to show you the proofs behind these, but we have a feeling you'll just take our word for it. These equations can all be found on that formula sheet, which again, if you're not printing it out, you should certainly be making one for yourself as we go along. So the derivative of the tangent of x is the secant squared of x. The derivative of the cotangent is negative cosecant squared. The derivative of the secant is the secant times the tangent. And the derivative of the cosecant is the negative cosecant times the cotangent. So again, you don't have to memorize these. You just have to know that they exist. And then, of course, use them appropriately. A little reminder here, just as always, it's good to remind ourselves of all the different trig identities and all the different things we might be asked to do along the way. So over here on the left-hand side, you have those reciprocal identities, your quotient identities, and then the Pythagorean identities. You are going to see a little bit of a use for the Pythagorean identities today. So as always, those are kind of the most important. And remember, just because this particular slide shows you the problems in terms of theta, it will work for any variable. Then over on the right, you have a reminder of how do you calculate the 6 trig functions if you're on the unit circle, which of course means that the radius is 1. And then here in the bottom right is a reminder of the 4 quadrants and then the values of the quadrantals. So 1, 0, which is at 0, 0, 1, which is at 90 or pi over 2, -1, 0, which is at pi or 180, 0, -1, which is at 3 pi over 2 or 270. And then, of course, once around the circle will bring you all the way back to the point 1, 0. And you could continue going around in multiples of 90 or pi over 2. If there are trig things that you're going to have to evaluate, which there are, you have to decide, do you want to be in radian mode or degree mode? I would probably recommend that you be in radian mode. That will work if you're inputting 0 or anything with a pi. If you're going to instead convert it to degrees, then you should be in degree mode. Here's a reminder of the entire unit circle. And again, remember that the cosines are your x values, the sines are your y values, the tangents are your y values over your x values, and then the 3 reciprocal identities. Something that I just want to point out here as a reminder, because as much as your calculator will help you, you have to make sure that you understand what it is you're plugging in. So let's say that you were being asked to find the sine squared of x. No matter what x turns out to be, you have to plug it into your calculator as the sine of whatever the value in question is, and then you have to square it. Let's say that you are being asked to find the secant squared of something. Again, even if you want your calculator to remind you of what the secant is, again, you could also look at this circle and that would help you. But either way, you're going to have to type that in as the secant of x and then square it. So the calculator is a great tool, but you have to make sure that you're using it appropriately. So let's go ahead and find a couple of derivatives here. And again, we may or may not be using the product rule for these first couple, but we will certainly be using our new trig rules. So find the derivative of y equals x minus the tangent of x. There are no products to be found, so we're just going to go ahead and take the derivative one at a time. Remember that you can either call it y prime or dy dx. I'm going to go ahead and call this one dy dx. The derivative of 1x to the first, bring down the 1. 1 times 1 is 1. X to the 1 less power would be 0. So the derivative of x is just 1. Then subtraction. Then if we go back a couple of slides, the derivative of the tangent is the secant squared. So the derivative of negative tangent is negative secant squared. while technically that is a fine answer, you should try to simplify if and when you can. So notice that here in the bottom right-hand corner, I have those three Pythagorean identities. So 1 minus secant squared, while that is not exactly one of the identities, if I was to rearrange this second one and move the secant squared to the left side, I would then move the tangent squared to the right side, and I could go ahead and simplify this to be negative tangent squared of x. If you're wondering why it is that we're doing that, again, eventually, sooner rather than later, we're going to be setting these answers equal to something and solving. And it is, in fact, much easier to solve if you have just a single term, like a tangent squared, as opposed to having multiple terms. So if and when you can simplify by reducing the number of terms, that's usually a good strategy. Notice that here in the next problem, it's almost identical except for the signage. So we'll call this one y prime. The derivative of negative x is negative 1. The derivative of a positive tangent, the derivative of a tangent is still secant squared. So this would be negative 1 plus secant squared. And again, if you take a look at this identity, if you were to rearrange it so that it's secant squared minus 1, that would actually be equal to a positive tangent squared. And again, when it's possible to go ahead and rewrite it as fewer terms, that would certainly be my advice. So here, take the derivative of x times the secant of x. So this includes not only the product rule, which I have up here, but it also includes your ability to know what the derivative of the secant is. And again, all you have to be able to do is look at it. So if you are continuing to find this little key that we've been setting up helpful, then I would continue to go ahead and use it. So your f would be your first function, which would be x. Your g would be the second function, which in this case would be the secant. The derivative of x is 1. The derivative of a secant is a secant times a tangent. And yes, you do need to have both. This is h of x. So the derivative of h of x is h prime of x. And again, using the product rule, it's going to be the first x times the derivative of the second, which is the secant plus the tangent. So first times the derivative of the second plus the second, which is the secant, times the derivative of the first, which is 1. From here, there's not too much that can be done. So you can go ahead and you can distribute that x, which doesn't really do much for you. It gives you x secant of x. Oh, sorry, this should be the secant of x times the tangent of x, not addition. Sorry about that. So this will give you x secant of x, tangent of x, plus the secant of x. And then again, while technically that is a fine answer, again, because of what's coming next, because you're going to want to set it equal to 0 or set it equal to something and then solve, the best way that you could give this answer would be to factor a secant out of each term, which would leave you with a secant times an x tangent of x plus 1. Again, it's unlikely that you would be marked incorrect if you had stopped one step earlier, but again, kind of setting you up for success in the future. It does make sense not only to reduce your number of terms in the answer, but also to factor when possible. And again, just make sure you know that this is secant times tangent. A little, trouble with the T for tangent is sometimes you get confused and write it as an addition. So sorry about that. Okay, take the derivative of g of t equals t to the 1/4 plus 6 cosecant of t. Again, t's aren't anybody's favorite variable, certainly not mine, but because of the fact that you are going to have to be answering questions with time and word problems, it is good to see them from time to time. There is not, however, any product rule required for this. Remember, 6 is just a constant, so if one of your f or g's is just a constant, you're just going to use the constant multiple rule, and there's no need for the product rule. So we're going to call the derivative of g of t, g prime of t. We're going to go ahead and bring down the 1/4. Then we're going to bring t to the 1 less power. So 1 less than 1/4 would be 1/4 minus 4/4, which would be negative 3/4. The derivative of a cosecant is a negative cosecant cotangent. So positive 6 times a negative cosecant of t, cotangent of t. So then I'm going to go ahead and clean my answer up a little bit. So 1/4 t to the negative 3/4. I'm going to leave the 1 on the top. I'm going to leave the 4 on the bottom. And then I'm going to turn the exponent positive by making this into t to the 3/4. And then 6 times negative cosecant cotangent. I'm just going to write that as negative 6 cosecant cotangent. And that would be my final answer here. Again, while I could find a common denominator, it actually would not do anything for me in this case, so there really would be no good reason to do so. Here in the next example, find the derivative of h of x equals x squared times the tangent of x. So again, this is where we have to use not only our new trig rules, but also the product rule. So if you're using this key, you're going to go ahead and call f x squared. Then you're going to call g the tangent of x. The derivative of x squared is 2x. The derivative of the tangent is the secant squared. The derivative of h is h prime. So we're going to do the first, which is x squared, times the derivative of the second, which would be secant squared x. So first times the derivative of the second plus the second times the derivative of the first. So the second is the tangent of x times 2x. And again, as I've mentioned in my previous lesson, you can go ahead and invert those just so that they look nicer. The tangent of x times 2x can also be written as 2x times the tan x. And since that's how we're more used to seeing it, it does make it a little bit easier in terms of finding the common factor. But again, either way would be fine. Here for the final answer, again, there's not incredible amount of stuff to do, but if you go ahead and look at each of these terms, remember that terms are separated by pluses and minuses. You can go ahead and factor out the common factor, which would be x, which would leave you with x secant squared x plus 2 tan x. If you're wondering, thinking to yourself, these answers are not the nicest answers, they look relatively complicated, that is definitely true, not only for product rule, but certainly anything that's involving trig. So don't be surprised if you do get those kind of messier types of answers. Now that we've seen our new trig derivatives, and now that we've practiced our product rule for the second day, we're going to go ahead and talk about the quotient rule. Here's something that you should know about the quotient rule. It escalates very quickly. There are easy and straightforward quotient rule problems, and then there are problems that turn into a big old mess. Because of the fact that it would be very difficult for you to not only completely accurately answer the more difficult quotient rule problems, but then also to type them in correctly to Edge Elastic, we're only going to do easier versions of the quotient rule for this upcoming test, and then we're going to give you a separate opportunity to practice the harder questions. So you're not going to see any questions on the upcoming assessment that are any more difficult than the ones you see today or the ones that you see tonight. So just keep in mind that we are going to do the harder quotient rule problems, but not until after this assessment. So here's what the quotient rule says. If you're taking d dx, which of course, again, means the derivative in terms of x, of some f divided by some g, you're going to take the g function, which is the denominator, times the derivative of the numerator, minus, make sure you notice that it's always a minus, that's just what the formula says, minus the numerator times the derivative of the denominator, and then that is all over the denominator squared. So give you a second to write that down. And again, hopefully you can see or understand why just looking at the formula, you can probably understand why it would escalate quickly. So again, we're only going to kind of do some basic problems, and then we'll save the harder ones for after the next assessment. So let's go ahead and try one. So find the derivative, and then most importantly, simplify. Most people, without a doubt, are able to just plug in the values into the formula, but it's more important than ever, especially for what comes next, that you're able to simplify. So here's a little reminder up at the top what the quotient rule is. And again, the F and the G setting up this little key is still a great strategy for the quotient rule. So we're going to go ahead and continue to employ that, at least for now. So if you're doing F and G, then you're going to go ahead and make the F your numerator, which in this case would be x minus 1. Then you're going to make your g of x your denominator, which would be 2x plus 3. Notice that both of these functions are just linear, which means that the derivative of each will just be a constant, which means it's really kind of nice and simple, which again is the type of problem that you should expect to see, at least for now. So the derivative of x to the first, that's just 1. The derivative of a constant is 0. The derivative of 2x is 2, and the derivative of 3, which is a constant, is 0. So we're going to go ahead and call this dy dx. And again, you could also call it y prime. It doesn't really matter. So if we use the formula, you're going to start by multiplying the g times f prime. So that's going to be 2x plus 3 times 1. Then always a subtraction, x minus 1 times 2. And again, feel free to invert those if you want to make it just a little bit easier to see. All over the denominator squared. So the denominator squared is the quantity 2x plus 3, and you're going to go ahead and square it. So that's just the simple application of the formula. And now we have to go ahead and try to clean things up as best we can. So by clean things up in this case, we're going to go ahead and look at the numerator. So we're going to multiply 2x plus 3 times 1, which of course would just be itself. Then we're going to distribute this 2. And again, don't forget about the minus, which again is why it's sometimes easier to put the 2 out front. So I left myself a little bit of extra room here since I thought that I would need it. So again, we're doing dy dx. If you distribute the 1, you're going to get a 2x plus 3. Then if you distribute both the negative and the 2, you're going to get negative 2x, followed by positive 2. And again, this is all still over the denominator squared. Seems hard to believe, but you wouldn't be surprised at how often people just forget about the denominator squared. So certainly try not to do that. And then for your final answer, dy dx, notice that on the top, the 2x's cancel, 3 plus 2 is 5. And you do not have to FOIL out the denominator. When we say simplify, FOILing out the denominator is actually not making the problem simpler. Especially as we get into the quotient rule, feel free to ask your teacher, do I have to keep going or is this far enough? Because often people try to go too far and then they wind up making mistakes. So there is no need to do that. So that was your very first quotient rule problem. And again, you could see why it was relatively simple, given that both the numerator and the denominator were linear. Let's go ahead and take a look at this one here. So y equals the sine of x over x. Again, that is now something that requires the quotient rule. You'll notice that that was familiar. There was a limit formula for the sine of x over x. That's a completely different question, so we can't use that here. But if you were wondering that it looked familiar, it is. So let's go ahead and apply our quotient rule, which would make our f the sine of x, and which would make our g just x. The derivative of the sine of x is the cosine of x, and the derivative of x is just a 1. We'll go ahead and call this one y prime. So we're going to go ahead and start with the denominator, which is x, times the derivative of the numerator, which is the cosine, minus the numerator, which is the sine, times the derivative of the denominator, which is 1, and that's all over the denominator squared, so that's just x squared. And again, do you have to put the 1? I mean, obviously, you know that it's a 1, but we're just trying to, at least for now, I'm trying to make sure you understand where the different parts are going. And again, there really isn't anything at all that can be done to simplify here, other than the fact that I can get rid of that 1 if I want to, and write this as x cos of x minus sine of x divided by x squared. There are no common factors that I can pull out. There are no reductions that can be done. Please make sure that you're aware that, let's say that the sine of x had an extra x in it, you would be able to reduce an x from each of those, but that's not the case. So that's our final answer. And again, quotient rule problems certainly wind up looking very messy in their final answers, even after you try to simplify them. So don't be freaked out by whatever kind of answer that you might get. Our final problem of the day, we're going to go ahead and find the equation of the tangent line to this function at x equals 2. Notice that here I clearly have a quotient, which means I have to go ahead and use the quotient rule. And notice that I have a linear function in the numerator and I have a quadratic function in the denominator. So this is already going to escalate a bit. And then we can't forget to actually take the derivative and go ahead and then find the equation of the tangent line. So let's go ahead, as always, by making our little key. So 5x minus 2 and x squared plus 1. The derivative of 5x minus 2 is 5. The derivative of x squared plus 1 is just 2x. We're going to go ahead and call this y prime. And we're going to go ahead and use our formula. So the denominator, x squared plus 1, times the derivative of the numerator, which is 5, minus the numerator, 5x minus 2, times the derivative of the denominator, which is 2x, all over the denominator squared. So that's x squared plus 1, the whole thing squared. And again, I am trying to show you exactly precisely where each of the values, f, g, f prime, and g prime, go into the formula, but you would certainly be able to invert these or invert these if you're trying to make your life a little bit simpler in terms of multiplying. Just make sure that you don't try to invert these, because that is not allowed. Okay, you have to make sure that the first quantity is before the subtraction sign and that the second quantity is after the subtraction sign. So again, I'm going to go ahead and give myself another screen here. So if I distribute the 5 times x squared plus 1, that gives me 5x squared plus 5. If I distribute not only the negative, but also the 2x to the 5x minus 2, that's going to give me a negative 10x squared and a positive 4x. Again, this is just the numerator. Then I'm going to go ahead and bring back in my denominator. I'm just kind of saving myself a step there. So from here, if I go ahead and combine like terms, I have a 5x squared and a negative 10x squared, which gives me a negative 5x squared plus 4x plus 5. And again, that's all over the denominator squared. So take a look at your numerator. There's nothing that is common or easy to factor out or reduce. So that is in fact my answer. Again, no need to FOIL the bottom. Now that I have found the derivative, remember that the question said, find the equation of the tangent line at x equals 2. So remember, now that you have the derivative, which of course gives you the slope of the tangent line anywhere, you want to find particularly where it's happening at x equals 2. So at x equals 2, you want to find the value of the derivative at x equals 2. So when you go ahead and do that, you're going to go ahead and get a value of negative 5 times 2 squared is 4, plus 4 times 2 plus 5, all over 2 squared plus 1 squared. Then go ahead and multiply. So that's going to give me negative 20 plus 8 plus 5. And that's all over 5 squared. So negative 20 plus 8 is negative 12. Negative 12 plus 5 is negative 7. And then 5 squared is 25. So negative 7 over 25, that would be my slope of the tangent line. Remember that in order to find the equation of a tangent line, you need not only the slope of the tangent line, but you also need the point of tangency. So let's go ahead and, again, I have another screen here. So the slope of the tangent line we just found was negative 7/25. The point of tangency, remember, was 2 comma something, and the point of tangency has to come from the original. So the original function was 5x minus 2 over x squared plus 1. So if I plug a 2 in, I am going to get 10 minus 2 over 4 plus 1. So that looks like 8/5. So I have my slope of the tangent line. I have my point of tangency. So y equals mx plus b. So 8/5 equals negative 7/25 times 2 plus b. 8/5 equals negative 14/25 plus b. Sorry, that's still just 8/5. I do, however, want to find a common denominator. So I'm going to go ahead and take 8/5 and multiply top and bottom by 5. So that's going to give me 40/25 plus 14/25. And that's going to equal my b, which means that b is a total of 54/25, not something that can easily be reduced or simplified. So my final answer, the equation of my tangent line, is y equals negative 7/25 x plus 54/25. And again, maybe you can see it, how the quotient rule certainly is going to escalate quickly. So again, this is kind of the hardest that you would see, not only on tonight's homework, but also on your upcoming assessment. So here is calc homework number 13. I separated for you not in terms of numerically, but in terms of what the question was asking. So questions 44, 49, 50, 53, 60, and 67. Those are the questions where you're going to do your trig and product rule. And then 7, 8, and 11 are the only problems where you're going to go ahead and try the quotient rule. So thanks very much for tuning in, guys, and we will catch you next time.